All right, let's take a look at some tricky integrals. Each one of these have their own subtle technique. They're not U substitution nor necessarily. They're not logarithms. They're not trig rules. They're not any of the kind of standard integral procedures. But they all have their subtle little strategies, and I want you to be able to first recognize what they are, and then be able to handle them. So this first one, x squared plus 5x over x cubed. It might look at first like it's a U substitution problem, but it's not. This plus 5x kind of screws up everything. We can't make this U and turn that into a du. So it's not going to be a natural logarithm like you might think because it's a cubic over a quadratic. But what it is, though, is a super easy problem if you notice that the denominator is just one term, right? We can split this up into two separate fractions. So we can integrate x squared over x cubed plus 5x over x cubed. And I'm just algebraically splitting up a fraction. I'm not doing any calculus. I'm going to go ahead and simplify this. This is just x squared over x cubed. That's just 1 over x. And this is plus 5 over x squared, excuse me. And then I'm going to do those integrals. 1 over x, the integral of that is just the natural log of x. And the integral of this power, I increase the power to -1 divided by the new power, so minus 5 over x. Okay, this is what I call split them up. Split them up, right? I mean, you can split them up. Certainly, it's the easiest to split them up when this is just one term. So anytime you just have one term down here, it's pretty easy just to look at that fraction and that fraction as separate integrals. Do the integrals separately after you've simplified them, and all of a sudden the integral is really easy. Similar strategy down here. This is the square root of x and x plus 4. It's like, what do I make? Do I make that u and then that's going to be all weird? There's no real strategy for like a u substitution, but if you just multiply it out, think how easy it is then. Just go ahead and multiply that square root in. The square root of x times x is x to the 3 halves plus 4 square root of x. And now they're totally separate. Now we can just integrate them as normal. Increase the power by 1. Divide by the new power. Dividing by 5 halves is multiplying by 2/5. Plus 4. Increase the power by 1 was a half. Remember, the square root of x is just x to the half. Increase it by 1. Divide by the new power. Again, dividing by 3 halves is multiplying by 2/3. I'll go ahead and write it over there because I didn't really have room. Plus c. And then we can simplify that. So that's equal to 2/5 x to the 5 halves plus 8/3 x to the 3 halves, of course, plus c. And again, if you want to check, you can take derivatives of this and then you'll get back this, which is the same thing as this. Again, this is x to the half power, x to the first power, multiplying together, you get x to the 3 halves, x to the half times 4, of course, is just that. Again, so this is what I would say, hey, just multiply it out. Just multiply it out. Turn a product of two things into just kind of separate functions. Okay, so let's multiply it out. This one is probably my least favorite. Okay, you can't make u sine and try to do power rule because you're never going to have du, which would be cosine. You would need a cosine here, and you don't have it. So there's nothing you can do except you can remember a trig identity. Sine squared is equal to 1/2 minus 1/2 cosine 2x. And the worst part of it is you just have to memorize that. There's probably nothing you're going to do to actually remember it other than just committing that to memory. Sine squared is equal to that. I didn't do the integral yet. I just rewrote sine squared as an identity. And then I can integrate this identity because the integral of 1/2 is just 1/2 x. And then the integral of 1/2 cosine of 2x. Well, the integral of cosine, right, negative cosine, is going to be negative sine. And since the chain rule applies, this would be the reverse chain rule. I'm going to have to divide by another 2. This was already half. Dividing by another 2 is going to make this minus 1/4 sine 2x plus c. Okay, and every now and then, the only way to do an integral is a trig identity. Okay, the two main ones are the fact that the one we just did, sine x squared is the same thing as 1/2 minus 1/2 cosine 2x. Again, that doesn't do the integral for you. That just rewrites sine squared, but then you can integrate that. And then cosine squared is easy because it's 1/2 plus 1/2 cosine 2x. The only difference is this sign here. Again, both of them turn into cosine 2x's, of which you can integrate using a little u substitution. Okay, so this one, split them up. This one, multiply it out and then integrate separately. And this one, unfortunately, you just got to use a trig identity to change sine squared or cosine squared into this and then integrate that result. Okay, I'll do two more. Right, this first one, see how this is an x plus 1 and this is an x and they're the same power? Huh, it's not really that much you can do with it, except, unfortunately, you can do long division. Long division. Okay, you can change this algebraically. So what we're going to do is we're going to bust up old school and do x plus 1 dividing into x. Okay, that's what this is saying, right? X divided by x plus 1. X plus 1 goes into x one time, and then multiply x plus 1, and then subtract. And when you subtract, this is a 0. Minus 1, you get minus 1. And then that's your remainder, so a minus 1 over x plus 1. And again, what I'm saying is that algebraically, x plus 1 is the same thing. What we're claiming here is that this is equal to this. I just use long division to change it into a different algebraic form. And again, think about it. If you wanted to recombine this to prove it's this, if you multiply top and bottom here by x plus 1, you'd have x plus 1 minus 1 to give you x all over x plus 1, and you'd be back to this. Again, that's an easy algebra proof to show that those two are equal. So instead of integrating that, I can integrate something that's completely the same thing as that. But that integral is really easy. The integral of 1 is just x. And then this integral is just minus natural log x plus c. And again, every now and then when these two powers are the same, you end up using long divisions. You got to go like all sixth grade on somebody and go long division. Turn this into this and then evaluate the new integral because again, you changed it into a form that you know. Okay? And then this last one is like back substitution. Okay, so it's similar to u substitution, except we have this weird term out in front. So we have something and we have something to some major power. So we can let u equal to x plus 1, which means du is equal to dx. But this also implies that u minus 1 equals to x. Okay, and look what it allows us to do. The integral of, instead of x, I can write u minus 1. So I get u minus 1 plus 3, and then this is just u to the 7th. Dx is just du. And you see how this used to be two things multiplied by each other? But look what happens. This is just u plus 2, u to the 7th du, and I can just multiply that single term in and make this u to the 8th plus 2u to the 7th. And now I can do power rule. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power, and then I can put u back in. Remember, u is sitting right here. U is x plus 1, and so I know it looks a little messy, but it's x plus 1 to the 9th over 9. And this is just 2/8 is just 1/4, so that's just x plus 1 to the 8th all over 4 plus c. And that is way easier than if you actually multiplied this whole thing out, x plus 1 to the 7th, multiplied it by x plus 3, turned it into some massive polynomial, and then try to integrate the polynomial. You'd get the right answer, but it wouldn't be as simple as looking something like that. Again, this is called like back substitution, where you make this u, you can turn that into u to the 7th, but if u equals x plus 1, then u minus 1 equals x, and then you can take that u minus 1 and put it in for this x. And so you've gotten rid of all the x's. You've gotten rid of this, and dx, and you have an integral with u's. Then you can multiply this in to turn it in from a product into two terms. And once you have two separate terms, you just integrate them separately. Again, those are 5 different kind of strategies. And again, see if you can see them all on one page here. Can you see all those? You can split things up. You can multiply things out. You can use trig identities. The 2 trig identities I need you to know are sine squared and cosine squared. We can use long division to manipulate things in order to change the integral. And then we can do some sort of back substitution. Okay, so that was kind of me walking you through 5 different integrals that are not necessarily the standard integrals, but I need you to be able to do them.